Hello, and welcome to this MCMA webinar. Integrating Controls and Safety Provides Protection and Productivity. My name is Joanna Keel, and I am the Manager of Marketing and Membership for the MCMA, and I'll be serving as your moderator today. Attendees that have joined this webinar have joined in listen-only mode, which means that you are muted. If you do have a question during the webinar, please submit them in the questions panel of your webinar screen, and we will answer all questions via email after the webinar today. As a reminder, this webinar will be recorded and a link will be sent to you within the next 24 hours. And now I'd like to introduce our sponsor of today's webinar, Kollmorgen. Since its founding in 1916, Kollmorgen's innovative solutions have brought big ideas to life, kept the world safer, and improved people's lives. Today, its world-class knowledge of motion systems and components, industry-leading quality, and deep expertise in linking and integrating standard and custom products continually delivers breakthrough solutions that are unmatched in performance, reliability, and ease of use. Products like Kollmorgen's AKMH, hygienic servo motors, PMX series stepper motors, AKDN, and the PCMM standalone motion controller gives machine builders around the world an irrefutable marketplace advantage that provides their customers with ultimate peace of mind. And I'd like to introduce our presenter for today's webinar, Kristen Lewatsky. Kristen is a contributing editor for Motion Control Online and has written about motion control and automation for more than 9 years. As a technical writer, she covers a variety of subjects ranging from memory and microelectronics to nanotechnology to laser and photonics. Kristen previously worked as an engineer on NASA's Chandra X-ray telescope before switching to writing about technology. Kristen holds a Bachelor of Science degree in physics and a master's in optics and photonics from the University of Central Florida. And with that, I'd like to hand it over to Kristen to get us started.
Thanks, Joanna. Thanks also to the sponsor, and thanks to everybody out in Radio Land. So let's talk about safety. When I first launched into the idea of doing this article and webcast late last year, I was figuring, okay, time to cover safety again. Let's do kind of an overview. We'll see some overarching trends. Outside of a greater trend towards safety uptake, the main trend I saw was there is no overarching trend. There are so many options out there for OEMs, machine builders, end users to adopt safety and to their particular application, that the way I'm covering this is less about talking about overarching trends, is let's take a look at what some of the different aspects of safety that you can buy today will actually do for you in your system. But first of all, we should probably look at the overall evolution of safety. It started out years ago with the aim of protecting operators, obviously from damage and mayhem and that sort of thing. It evolved subsequently into functional safety. I'll talk about that. That's much more of a systems-oriented rather than device-oriented approach towards safety. And then here more recently, the components and functionality that have enabled kind of the latest generation of functional safety are really being advanced by integrated safety. By tying things together, that's where we get the real benefit. And again, that's kind of the main thing I'll be talking about today. Philosophy of safety, kind of the overarching way to think about safety is really that you want sensors out there. They are looking to detect anomalous behavior by the operators of machines. What happens next is not necessarily defined by a specific state. It's really the goal of getting the equipment and the machine to a safe state, some sort of a known safe state. For example, if you're talking about the field bus aspect, if you're using some sort of a machine-based network, the safety philosophy there is that the system really just needs to know whether there is a flaw in communications. If it detects a flaw in communications, its job is to bring the machine to a known safe state so that nothing bad can happen at that point. So, that's really kind of the underpinning behind all these systems we'll be talking about today. Traditional manufacturing was kind of the same thing we've heard about over and over again: fixed machines, consistent product. You've got companies manufacturing the same thing 24/7, dedicated line, and safety was very much from the standpoint of protecting operators. You want to separate people from motion. You want to make sure that they can't get hurt. And that was something that could be implemented very statically because you had the fixed machines, you had the consistent manufacturing. The overall design was very much to place safety within the devices. So you put up a barrier, you put up a light curtain, you put in a pressure mat, and the idea was pretty much go, no go. And you might use a controller to make all of this happen. Typically, things were hardwired back in the day, and you wind up with, basically cut power. If something happens, somebody walks through a light curtain, they open up a barrier, you get a door interlock, your relay goes bam, and the system shuts down. And that, of course, can be a problem if what you're doing is trying to manufacture stuff. And that's where you kind of wind up with this sort of uneasy relationship between safety and productivity, because on one hand you want to protect operators, but part of the act of protecting operators means shutting down the line and your safety 1.0 kind of implementation. Productivity goes down, throughput goes down, and these days there's so much focus on OEE that people are really looking at those numbers, and unfortunately what you can wind up with is operators well-meaning and sort of focused on, hey, do the best for the company, do the best for their shift, trying to do workarounds. We'll talk more about that in a minute. But that's particularly become an issue these days because manufacturing is different today than it ever used to be. Everybody's looking for customization. We're all after the fabled batch of one, where you can get people exactly what they want, and that means that you've got your lean inventory, you've got manufacturing on demand. You need to be flexible. You need fast changeovers. You need frequent changeovers. That means your operators need to potentially get in and access equipment. Your maintenance people potentially need to get in there as well. And unfortunately, what happens is you get people wanting to, again, find up workarounds. One of the people I interviewed a month or two back for the article I wrote said that she absolutely hates relays because they're so easy to rewire. She says, people can do a workaround and that's taken care of, and maybe it lets people keep running the machine while they're opening enclosures and stuff. But and if you wind up with situations where you had static manufacturing, like in this example, you've got something falling off a conveyor belt, and maybe if you had a consistent 24/7 dedicated line, you'd put up a guard and you keep those boxes from falling out so people wouldn't get irritated that they keep having to stop the line and go in and pick up the box, restart the line, lose numbers and all of that. But if you're constantly switching around inventory, maybe that's not practical. So what happens? You wind up with people, getting the bright idea to rewire the relay or bypass the interlock. Maybe they forget to switch it back. Maybe it's just easier to leave it that way. Now you've got engineering and management. They think the area is safe. Somebody's going to get hurt one of these days that doesn't know about it, kind of thing. And like I say, she was seriously ranting about how much she doesn't like them because she thinks it's dangerous. Going to smart safety gives you a much better way of attacking these kinds of problems. So that is part of what sort of led to the evolution toward functional safety. And the idea there, for those who are familiar with it already, is it's very much putting safety in the function of the system. So instead of safety kind of residing in the component, say a pressure mat, you step on it, bang, it's going to stop the machine. Now it's the safety in the operation of the system, which goes back to what I talked about at the very beginning. You've got the philosophy is to create the safe operation of the system. If something or someone goes outside of the operating parameters that you set, the machine needs to recognize that and go to a known safe state. So that's very much systems-based. Now, it's important to note, even though functional safety has really become tightly associated with some of the more sophisticated techniques we'll be talking about, it can and is implemented with basic safety components like we've been talking about and implemented with relays. And that might be the best approach. So, certainly one of the things they took away from this whole project is there's, as with pretty much anything in engineering, there's no one right answer. And there are systems out there, relays are the right way to do it. That said, smart components can make a big, big difference in functionality and everything else. So going on to modern safety equipment, the idea is still, let's protect operators from injury, but safety is a much broader definition than that. It's about protecting equipment from damage, and these days it's also about protecting revenues and performance. It's as much about, first and foremost, it's about protecting human beings, but after that, it's really a profoundly powerful tool for protecting the bottom line. So as far as the safety standards that underpin that, anybody who's looked into this, there are dozens of them out there, but the key ones for the purposes of this discussion that we really care about, IEC 61508, that's the primary functional safety standard, and it defines the safety integrity level framework that sets a limited number of errors in the -6, -8 levels, so that you have to be able to have equipment in place and tested to operate to those levels. 62021 is kind of runs through the implementation of 61508 and is particularly applicable to motion control. If you want to swing toward ISO 13849 is the ISO version of functional safety, and its version is safety performance level. So if you look in the various functional safety standards, part of what is really valuable about them is that they define a number of much more nuanced functions. Now, most people are probably familiar with safe torque off. That's gotten to where it's pretty much a standard. Not every drive shift has safe torque off, but an awful lot of them do. And it's really specified into a lot of machines. What happens with the rest of these functions, it really depends where you're at and who you're dealing with. In Europe, the functional safety standard is a regulation, so you wind up with a lot of broad use of some of these functions I'm going to be talking about here in a second. In the United States, not so much, but that is increasingly being adopted as end users and OEMs are starting to really recognize the value of having some of these functions. So you've got, your safe torque off. You've got a safe stop that sets up a method for safely braking high kinetic energy equipment, but doing it quickly. and that sets it up for safe torque off. And the key point about safe torque off is, unlike your relays that just cut power, safe torque off takes torque off from the motor via the drive. You don't actually shut down the equipment, and that means that startup is much faster. It's also easier on the equipment. So you've got safe stop that sets you up for safe torque off, but then you've also got safe operating stop, which if you're using the servo drive and you've got good feedback, you can hold your drive or your motor at 0 speed. You don't even have to remove torque as long as you've got, everything, again, is properly specified. So you've got safe operating stop that lets you put the equipment at a standstill and be ready to jump right back into operations immediately. Safe stop 2 is what sets you up for safe operating stop. Another safety function, external holding brake. That's important, especially for motors holding loads on vertical axes. And then the next 3 are the ones that are really interesting. And take it, there's a bevy of other versions of these functions, but I'm just kind of presenting a selection. But safe limited speed, you can set up a maximum speed so that you can only go to a peak level. You can also set up a speed range, high and low, that your drives can only command the motors to run between that speed range. Safe direction, that means that you can only turn, if you have a rotating axis, it can only rotate towards you or away from you. Again, you've got the ability to really constrain motion. Safe limited increment, you can support jog operations. So what these things can do for you is when you're doing operations, cleaning operations, or if you've got a jam or whatever, then you're able to only have rollers move away from the operator. So the operator can use safe limited increment. They can clear the jam and do it in a way that doesn't present any hazard to them, but also speeds recovery. It means it uses the machine to do the recovery as opposed to having the operators have to get in there. So things happen faster, better productivity, everything's safer. So let's take a look at a couple of examples on what that exactly means. If you've got a printing machine, you have to clean the rollers, right? And if you want the old school approach, that's clean the section, then you step out, close the enclosure, start things back up, you jog the machine, you come in, you clean, and then, now that you've got your interlock coming into place, shuts down the machine, repeat over and over. Now you can use safe direction, safe limited speed, and you could be in there cleaning it continuously. And you can have specific cleaning modules to let you do this automatically. So, less time cleaning, more time making stuff, higher OEE, we like all that. And here's a particular case study, food and beverage. So this was a company that spent time doing the clean and jog cleaning, and 6 hours a day they spent just cleaning. And they implemented a version with safe speed, safe direction. They used safe position protocol, which limited the safe operations when the enclosures breached. It cut the cleaning time down to 1/3 of the previous time. That's an extra half shift of production. Another example, electronic fuel injectors. And that was something where the operator had to break the light curtain to adjust the part, and the machine pulled away. Now the end user / OEM, they were already using safe limited speed, and that speeded up things a certain amount. But the thing they realized is, because of the application, what was really important is, or dangerous, was motion toward the operator. when it was motion going away, it didn't matter, so they could go top speed instead of pulling away at safe limited speed. And again, 10% reduction in cycle time. 10%, you can take that money, you can increase capital without, you can increase production without higher capital. You can maintain production with fewer operators. You can take that time for preventive maintenance. 10% is a big savings. And that's the thing to keep in mind with these kinds of systems. And the sense I get talking to integrators and OEMs and folks out there, the end users even that I've spoken with, people are starting to get the fact that you have big savings. You can get ROI on this. You get lower total cost of operations. And that's something that's of increasing interest out there, especially in the end user community, because you can get that savings. You got to get everybody involved in the specifying. If you're just going in through engineering, you're probably not going to get much buy-in as far as cost of ownership. You might get buy-in as far as uptime and productivity, but the thing to keep in mind is you can go so much farther than safe torque off. So it's really a competitive advantage angle. And the kind of the buzz that I'm hearing is in the next couple years, it really is going to start seeing huge levels of uptake. There's already a significant uptick. So the thing to do, again, and I was just kind of ranting about this, but it kind of changes the way we're looking at safety. Safety was a response. The anomalous behavior hits, we cut power. But at this point, it really becomes more of a process. This behavior happens, here are the things that we do. Here's how we respond. Here's how we go back to that earlier comment I made. Here is how we make sure that the machine goes to a known safe state. And maybe that known safe state is, as I talked about in the earlier examples, it pulls away at top speed, but only in a safe direction. So a known safe state doesn't have to be safe torque off or safe operating stop. A known safe state can be just constrained operations that let you get done with what you need to do without putting anybody at risk, and also without putting your production at risk. So safety components, kind of the key thing we care about there is you really want to be thinking in terms, obviously, of reliability. It doesn't do you any good to have a safe system if the safe system fails. The other thing you need is redundancy, because if you've got a safe system, but it winds up with a failure mode that matches the failure mode of some other part of the system, then it's not going to be able to detect error. So that's really the key thing that you always have to be thinking in terms of is how do we avoid common cause failure. Drives and controllers, which are kind of lie at the core, pardon the pun, the core of safety. You wind up really working in terms of dual core processors, and that's key to make sure that your safety calculations are, number one, happening in two different physical locations with two different physical pieces of equipment. But that alone isn't enough. Remember, we're talking about that common cause failure. You've got to be using different logic. In most cases, or in many cases, you have different chips. You can even potentially be using different manufacturers. The language that gets used a lot is homodyne versus heterodyne. If you've got a drive with a dual core processor, is it homodyne where you've got identical cores, or is it heterodyne where you've got two different cores? And in that case, if you've got an interpolation error that's common to a particular processor, you don't want that to affect your safety. But that said, if you're using a different algorithm and then checking to see that you get the same response, maybe that takes care of using the homodyne version. So as much as anything, picking the right safety system comes down to knowing the right questions to ask and making sure that you're picking the right system for what it is you're trying to do. Encoders, same thing. We want redundancy. You're going to have an encoder, your safety rated encoders. You're going to have digital absolute, incremental analog sensors. They're going to record data over 2 different channels. And the idea then is you get your data streams arriving at the master, and that's going to get analyzed differently there. The goal being with all of this is once it arrives there, that you're able to get the same information. Now encoders, there are a lot of different sensors involved in safety systems. Certainly as I was talking about before, you've got light curtains, you've got barriers, you've got interlocks, you've got proximity sensors, and all that sort of thing. But particularly with functional safety, encoders play a huge role because that's the technology that can let you know whether, if you're invoking safe limited speed, somebody's got, or a component has to close the loop with the motor and either the drive or the controller or both to make sure that you're not exceeding those numbers. You've got to have something that can monitor your safe direction and so on. So encoders really play a key role, and you've got to have that level of redundancy. Software, same thing. You've got to, as I mentioned, use multiple different algorithms. You'll have internal checks. You need to verify equipment's installed and operating. In a lot of cases, checksum codes can be used to detect anomalies, also to detect whether changes have happened to the code. You'll want to use permissioning, access limited by job role, so that some people, engineering maybe can save changes, maintenance can only view, operators can only view, that sort of thing. And again, it's just that theme of protection, protection, protection. So, as I said earlier, you can do functional safety without smart components, but you really need the smart components to get the best. And to get the best from the smart components is where we really start looking at integrated safety, because that's what brings it all together. That's where you start getting large benefits in terms of speed. You're going to get faster response. You're going to get easier implementation. In a lot of cases, you can use less hardware. You can get, because of that faster response, maybe the clearance distance or offset that you have to use is not going to be as large because you don't have as much latency involved. So, and it goes back to that same thing. You can keep everybody safe, but you can also keep the bottom line safe. Because ultimately this comes down to productivity, and the thing that is really worth investigating in all these systems is, finding out just what the ROI is, what the likelihood is of getting savings, how quickly you can pay for that system. And you might be quite surprised. So integration levels go at a couple of versions. You've got integrated software, and that's pretty common in terms of having an integrated software environment that makes it easier to implement because the programmers and the users look and see the same thing all the time. But it also simplifies programming. In a lot of cases, you can get systems that will map variables over. So if you're defining variables in the safety system, they can automatically map over to the operational system. And that gets pretty detailed. And if you've got a complex system, you've got a high access count, you've got a large number of sensors, that can start getting tricky, making sure everything gets done. So being able to have integration is a big help. And it can be, just as simple as reset buttons, start commands that can really speed up troubleshooting. I was talking with a programmer who said, a lot of times you get troubleshooting going on and you've got maintenance running through all the screens, and if they're having to go separately between safety and operations, they're running through all the safety stuff first because they've got to, and then they find out at the end that it's actually the fault was invoked by the motion system, and it's just waiting for a command, and somewhere a variable got mapped wrong. So again, the level of integration with software can be really helpful. And that's just an example of one of the screens that you can look at and be able to see automatically the status of equipment. And this is where we get to the interesting part, because when I started into this, I was trying to figure out kind of what the basics are with trends and so on. As I said, no general trends. So let's start with the general safety system implementation with the understanding that just as soon as I say this, there are going to be people out there in the audience raising their hands saying, wait, ours doesn't work like that. But in general, we start with sensors, we have a safety controller, we have the machine controller, motion controller, and the drives. Now take it, when I say machine controllers, motion controllers, this can be implemented pretty much any way you like. You got a lot of safety PLCs out there, and the rule of thumb really used to be with PLCs that they're good at counting, they're good at timing, they're good at I/O, and a little bit of motion, but not too much. If you have really sophisticated motion, you need a motion controller. These days, PLCs have gotten a lot more functional, so you can actually take them much farther. And as much as anything, it's what programming language are you more comfortable with using. The other implementation with safety is you've got safety PACs, or programmable automation controllers. So I'll probably lapse into mostly talking PLC to avoid having to run out all of them later on here, but just kind of keep in mind that it sort of encompasses the variety. Normal operation. So your normal operation is you're going to have your machine controller, motion controller combo, send commands to the drive. Safety sensors are out there. They're linked up to the safety controller. And the safety controller's job is really just to run the safety logic. So it's not doing any of the actual motor control or drive control to implement the safety commands. What it's doing is going through all of the safety logic to keep track of all of the conditions so that when it's got data coming in, it's able to determine what the right response should be. And if you've got a really simple system, that doesn't seem too hard. But if you've got, a 100-foot printing line with, dozens and dozens of axes, and you've got doors everywhere and interlocks, or it's a manufacturing line and you've got barriers and zone safety that you're implementing where certain areas are really sensitive to people getting in them and others are not, then you really need the safety PLC to take care of that. So then the safety PLC sends a command to the drive, tells the drive to invoke whatever state it's supposed to, and then the drive brings the machine to the known safe state. And again, when we're talking about bringing the machine to a known safe state, that doesn't necessarily mean safe torque off or safe operating stop. It can very well be, an operator steps into the enclosure to clean. That means we go safe direction. Let's go back to that roller example I was talking about cleaning. the operator steps in the enclosure, we invoke the cleaning routine, we go safe direction, we go safe limited speed. Those count as our known safe state. And the other key thing to keep in mind is these commands supersede the regular machine control commands. Now, these days you can do hardwired safety networks, but these days much more frequently you've got things happening over field bus just because it's faster, it's easier. And as I talked about earlier, you can think of it in terms of a black channel and set up your system so that even if there is a problem with communications on the network, the machine controller, whether it's your drive or your safety PLC/PAC, et cetera, recognizes, hey, we're not communicating anymore, bring the machine to a known safe state until this condition is corrected. And that might be your safe torque off, your safe operating speed, whatever those examples are. So it's most of your primary, actually I hesitate to use all, being trained in physics, but most of your communications protocols have some sort of safety version. And I did a tutorial last fall running through the main points of the main communications protocols. So they're all set up out there to perform this. And part of the key thing that you got there is that your safety messages have a header that makes them take priority over your controls. Now, the key thing there is there's still going to be a certain system latency, whether you're working with a protocol that takes regular polling or whether it's push notifications. There's going to be a delay in there, but that's where you do kind of your offset. So if you've got breaking a light or breaching a light curtain is the sensor that triggers the machine going into whatever safe state that gets invoked. You just need to make sure that the distance between that barrier and the place where the operator can be put at risk is long enough that the latency involved will pass, and your safety command is going to take priority and get in there before anybody can get close enough to get their fingers munched or anything else. Now, drives are, our first entry into, oh, it's complicated. Drives execute, nominally, they execute safety through the control of the motor. Now, these days, again, most drives that you can get, they're going to have safe torque off. You can do functional safety, even the kind of safety we've been talking about. You can do that with, quote unquote, dumb drives that are, able to do commutation and hand down path commands from the PLC and so on, but aren't set up to do any of the other kinds of features that we've been talking about. But you also have your safety-enabled drives. Safety-enabled drives have built-in functions, beyond just safe torque off, and some of them can take a high number of I/O, and then they've got the safety functionality, and in some cases, that's all you need. You don't, if it's simple enough, you don't need to program your system. You can really just configure the drive, and most of the ones that are that sophisticated will have functionality where you are able to easily configure it. So it's kind of a granimals sort of version to safety. So let's look at a few of the varieties out there. Here's one that looks at safety as kind of a decentralized I/O and really pushes through the drive. Up top, you see that you've got the safety I/O. And where is my mouse pointer? There we go. Yeah, so that's all your safety I/O. That is feeding into your processors. You've got your safety PLC there, and it's going to have your dual core because, again, you've got to have that redundancy. You've got to have something out there making sure that there's no one path that can fail. I mean, obviously, if, a meteor hits or something, you're not going to be able to be very redundant about that. But in general, the systems are sort of configured for logical redundancy. So anyway, and the red and yellow thing, that's all going through Circos-based system. So all of that input is coming into the drives. The drives are able to figure out what happens next. They've got the the safety PLC gives them the direction of what to do, and they've got the built-in functionality. The communication, again, takes place over Circos. You've got the precedence of your safety messaging, and in this case, the drives close the loop with the encoders. So the drive is what is monitoring whether, in the case of something like safe limited speed or safe speed range or safe direction, that the motor is behaving and it's not exceeding the area it's supposed to do. If the motor does get out of its required limitations, then again the drive can put the system into a known safe state, safe torque off, safe operating speed, whatever's appropriate, and wait for further direction. So that's kind of always the fallback. Anything that happens anomalous, worst case scenario, that the system gets put into safe operating state. If you want to go more centralized with your I/O, you can actually have your PLC, safety PLC, share a backplane with the regular PLC. You still have all of your sensor systems over here. They're communicating, in this case, with the master over ProfiSafe, but it's really only nominal. It's kind of like it's waving at the PLC on its way by, because in this case it's going over ProfiSafe. So it's really about sharing the communications link so that that information goes directly to the drives. And the drives are, with direction from the PLC to help untangle any logic if it's a complicated system. The drives are able to go ahead and monitor the conditions with the encoder. They're able to invoke whatever state they're told to by the PLC. Another version is to, again, you've got the redundancy here. You want to have a single, not a single, you want to have the dual redundancy, but this takes a little bit of a different tack to it that's kind of interesting, which is you've got one CPU for machine control and safety. Presumably on different cores, I don't know, they were reluctant to say, but you wind up with that CPU executing both machine control and safety logic on both of these. So the question is, where is the redundancy? The redundancy comes in from a separate outside CPU, backup safety CPU. So you got one PLC or controller that does your machine control and safety, and then you have your backup safety. That uses a different algorithm, compares results. If there's an anomaly, again, you get the same thing. Let's take the whole machine to a known safe state. And then you've got the, this should be Rockwell. Then you have you can kind of have it your way, as the Burger King commercial used to say. So you wind up with, your sensors coming in. You still have your logic. You've got the automation controller that's able to keep track. It takes input from the sensors and controls the drive, and puts the machine in the known safe state. And with this, you kind of have a variety of choices of whether you want to have the integrated safety and logic, or safety and machine control, or not. Another one is the drive-centric kind of approach. And that's going to be something where you've got a drive. It can take up to 8 I/O points. And this kind of goes back to what I was talking about earlier. You don't necessarily need to have a safety PLC in every system. You can have a drive handle the safety. It can take the I/O. It can undergo simple to even somewhat sophisticated decisions about what needs to happen next. It can close the loop with the encoder and be able to, really get the system into the known safe state, whatever that state might be. Now the question is going to be, what are your numbers of I/O points? If you've got a high number of I/O points, then maybe you need to rethink that. And that's kind of where the safety PLC comes into play, because the safety PLC can handle those high numbers. And with things like Zen Safety, you've got pieces coming in where somebody goes into an enclosure and maybe 5% of the axes, or the axes in this one area, this one module, need to go to the known safe state, but maybe the rest of the machine does not. And that's where you kind of want to have a safety PLC to really step in and handle that level of sophisticated motion, because it really kind of all comes down to maximizing productivity. So that's pretty much the sum total of what I found out about safety these days, but kind of the big takeaway is that there really is no one direction. And the key thing is to, if you're an end user, talk to your integrator, talk to your vendors. If you're an OEM, talk to your vendors, talk to your end user, find out what everybody wants, understand the application, because you've got a lot of different options out there. And this just scratches the surface. So thanks to our sponsor for sponsoring the opportunity. And thanks, Joanna, and thanks to everybody out there.
Yes, thank you, Kristen, and of course, thank our participants like you. I'd also like to thank our sponsor, Kollmorgen. As a reminder, we did have quite a few questions that came in during this webinar, so if you did have a question, please feel free to submit them in your webinar panel, and we will answer all of your questions via email after this webinar is concluded today. And also, I'd like to remind you to save the date for MCMA's annual technical conference. This year, the conference will be held in Minneapolis, Minnesota, October 16th through 18th. MCMA Technical Conference is designed for people working with motion control and motors, and more details, including the agenda and registration, will be released very soon. And lastly, for more information about upcoming MCMA webinars, please be sure to visit MCMA's website at www.motioncontrolonline.org. And with that, I'd like to thank you for attending today's webinar and enjoy the rest of your day.